I decided I should do a Northern Lights background because I know it is freezing cold up there in South Dakota right now. Uh, Let's start with a few facts about correlation, and then in the next video, we'll get into computing correlation. So a few facts about correlation. First of all, it is a measure of linear relationship between two variables. Talked about that last time. We talked about scatter plots, linear versus curvilinear. It ranges from -1 to a +1. And the correlation between x and y is the same as the correlation between y and x. Last time, we looked at a scatter plot of a perfect linear relationship. And if you have a perfect linear relationship, that means you have a correlation of 1.0, that the two scores vary exactly together. The lowest score on one variable is the lowest score on the other variable. The highest score on one variable is the highest score on the other variable. The middle score is the same, and so on. So that's a correlation of 1.0. A correlation of -1.0 is the opposite, in that the highest score on one variable is the lowest on the other. And so, again, you can predict perfectly from knowing one variable what this score on the other variable is. So in this example, the number correct is a perfect negative correlation of -1.0 with the number wrong. The fewer you got correct, the more you got wrong. The more you got wrong, the fewer you got correct, and so on. So there's a perfect negative correlation. And this is just an example of a correlation of 0.6. This is the correlation we saw before between the pre-test scores and the post-test scores. And this is a positive correlation. So correlations range from -1 to +1. If you see anybody that has, and I have seen this in publications before, that say they have a correlation of greater than 1, that is impossible. A correlation of greater than 1 is an error, because greater than 1 or less than -1 would mean that one score could be better than perfectly predicted from the other, which doesn't make any sense. This is a useless, in my opinion, very mathematical, but useless kind of explanation. A linear transformation is a function from one vector space to another that respects the underlying linear structure of each vector space. And if we're in a linear algebra course, which actually I like, we could go on about that. But here's a more useful explanation. If you report your student scores in number correct or percentage correct, it makes no difference. If you add or subtract a constant to every single score, that doesn't change the shape of the distribution. It doesn't change the correlation with any other variable. If you multiply every score by a constant, or divide, which is the same as multiplying by decimal, it also doesn't change the correlation or the distribution. And you maybe didn't think of it in the sense of you were doing linear transformations, but you probably have really dealt with this every day, because you know if you report your student scores as the number correct or is the percentage correct, it has no real difference. It has no difference in which students got the highest score, which students got the lowest score, how well your score is correlated to other things. If you add 5 points or more, or any number, if you add a constant to everyone's score, the relationship of those scores stays the exact same. It's a linear transformation. The highest score is still the highest, score in the exact middle, still the score in the exact middle. If you multiply every score by 100 or any other number, the relationship of those scores to each other and any other variable stays the exact same. So linear transformation does not impact correlation at all. You might wonder why I'm talking about this, but because it does become relevant and useful in a lot of situations. And that's a few things about correlation. We'll go into age of computing then in the next video.